All right, so today we are picking up where we left off on the other day, Tuesday. And we spent a good bit of our time the other day talking about outside the Earth, around the Earth, okay? Close to the planet and a little far out as well. Today, at least for the first half, we're going to focus on inside the planet, which, if you remember my opening story, is what sort of prompted this whole need for this. One of the big things that prompted the whole need for this is I got to the end of the semester one year and realized that I never taught them crust mantle core, let alone lithosphere and asthenosphere and all that. So we're going to talk a little bit about that kind of stuff, how and or why we know about it. And because we haven't really been there, right? Surface is easy to study, but stuff inside the Earth, that's a little harder. And then we're going to go sort of far out again, or at least way back go in the Wayback Machine and go back in time for a little bit. So, without further ado, I told you I don't like those spheres or zones, and you notice I didn't even use those words here. But we do want to acknowledge that the Earth at least has two primary sections, all right, the terrestrial and the aquatic. And again, this is superficial. I know I just did a whole prompt about how we're going to go inside the Earth, but at least for the moment, we're going to stay at the surface. And really just introducing two words you should know by now, and if you don't, it's time. Terrestrial and aquatic, all right? Or as I sometimes like to say, aquatic. Aqua, water, you know that one, right? And most folks are familiar with terrestrial, but when you start conjugating it, it's kind of, I like extraterrestrial, means from outside of the Earth. So that's really what that word means. Terra is the Earth. So we've got land, 30%, aquatic, 70%. When we do talk about water, which we will, you'll learn that a lot of that water is not directly usable for us, accessible, whatever word you want to say. As you know, we're covered mostly by oceans, which you can't drink without expending a whole lot of energy at any rate. Desalinization is a costly process. So we'll talk a little bit about that then, but for the most part, we're going to focus on the terrestrial. Yes, sir?
Is it true that we know more about space than we do about our own ocean?
You hear that quite a lot. I don't want to say it's easier to get there, because I really don't think it is, but
easier to research, right?
Well, indirectly. I mean, we could sit here with our telescopes and in our backyards all the way up to our giant telescopes on top of mountains and look wherever we want to look. Direct exploration, different question. The biggest thing with the oceans is they're so huge. I mean, not that space isn't, but again, we've been scanning that with our telescopes for centuries. So I don't know that you could say it's true or false, but yeah, I could definitely see what they're talking about. And just like we discover new things out in space all the time, the ocean is constantly surprising us. For sure. But, directly, and we'll hear some of this stuff, going all the way back to World War II, we did a pretty thorough scan of the ocean floor with the military and whatnot once we started, submarine warfare and stuff like that. So, not necessarily geologically or oceanographically oriented, but we've been poking around there for a while. Well, kind of just like the rainforest and stuff. They say the same thing about the rainforest. God only knows what's in there, and then there's a lot to that. So it really isn't that big, but still quite difficult to access. Radius. What does the word radius mean? Just to make sure we're on the same page here. Right. All right, from the center out, from the surface in, regardless, you better stop in the middle, okay? It's a spoke on a wheel kind of thing. So radius is not all the way across. Radius is if you wanted to go to the dead center of things. About 4,000 miles. Again, we got our little squiggly there. And we've been how far? 2. All right. And with great stress. I don't know if you've ever caught them on the Discovery Channel or Nature, whatever, any of those shows. See these folks coming up from diamond mines in Africa and stuff, and they look just toast, okay? They're in barely just loincloths. They're soaking wet with sweat, 85 pounds. There's probably other reasons they're only 85 pounds. But point is it's miserable, even 2 miles in, okay? It's hot. Feel some pressures. So us exploring as humans directly is tough. Now, we've drilled a whole hell of a lot deeper, okay? That's for sure. Drill bit is a different story. Don't have to worry about drill bits so much other than those diamond tips probably get expensive. We've gone a good bit deeper. I was talking with a couple of my buddies that went into like oil-related industries and whatnot. And they're like, oh, no, we could drill for miles and miles and miles. I'm like, no, not horizontal. They could drill horizontal as long as they want. But deep. He's like, oh, yeah, we haven't gone that far. And a lot of that time, they start at the ocean floor just because you've got that much less rock in the way. But then you have that whole floating platform and, the pipes going down to the... So that's wrought with issues as well. Now, I haven't checked these numbers super recently. I always give that disclaimer. Every so often I unofficially check, but I don't think I've caught anything that made me go back and say, oh, I really need to update that slide. And I've been teaching, like I said, a little over 20 years at this point. So there must be some huge things stopping us, okay? And like I said, basically pressure and temperature. We have, for those of you that pay attention to stuff, and again, it's more of a water thing, Challenger Deep. I don't know if you've heard of that. It's the Marianas Trench, okay? We've gotten pretty dang far, pretty dang deep in the oceans. So it's easy to confuse that with this. We're talking about drilling through solid rock, though, here, okay? It's not like we could go to the Marianas Trench and then go 2.5 more miles. So, a little different. Oops, too far. I like to give you these distance comparisons. This one isn't a whole hell of a lot helpful. But we had 2,000 miles, I think I showed you. Or was it 4,000? Let me go look here. 4,000 miles, sorry. All right. You got 240 miles to get to Manhattan. That's even not really helpful. I thought I had LA on here. How many miles is it from Utica, New York to Los Angeles, California? Even that is 2,700 miles. So you can't even go coast to coast. Okay, so this one maybe seems fairly deep, far for you guys. We were hopefully blowing your minds a little bit the other day with the atmosphere stuff, that it's not that far. But still, 4,000 miles. That you'd think it'd be a little bigger to the center of the Earth. All right. Mohorovicic discontinuity. Where's that word on here? That word on here is just under the crust there in white letters, and I don't ever expect you to write that word down. They call it the Moho line for just that reason. But Professor Mohorovicic would love it, possibly sick, Mohorovicic, but would love it if every so often his name gets remembered and mentioned, and not just shortened to the Moho line. So he did some work a ways back, and I usually talk, I'm not exactly sure when he did his work, but one of the things we noticed is when we started blowing up those giant, horrible, nasty bombs all over the place, that we were literally shaking the entire planet with the explosions. Some opportunistic geophysicists decided to take advantage of that and studying the world's largest earthquakes, as it were, and looking how the energy waves. All right, when we get to earthquakes, you'll hear the word seismology, seismic waves. You've heard seismologists, maybe. That's folks who study earthquakes. But that seismic energy, how it was traveling through the earth. Again, we've had earthquakes to study, but you don't know when they're coming and so on and so forth. But these you can sort of plan for. And as a result of that, they came to realize that there's this one particular place, one particular depth, that the energy waves changed velocity. It slowed down. So they're trucking along, and then all of a sudden it's like they got stuck in tar or something. And, we knew already that the inside of the earth wasn't the same as the outside of the earth. She does crack and bleed every so often. We've got volcanic events. So we knew there were differences, but again, not having the ability to go there, plus the assumption that with these volcanic events it's a lot closer than it usually is, or all of our groundwater would be boiling and so on and so forth. So this gave them the opportunity finally to say, oh, okay, at this depth, fairly evenly around us outside of the earth, we have a change in velocity, which equals a change in consistency of the material, which is, oh my gosh, let's call this the boundary between the crust and the mantle. Which, short story long, that's what the Moho line is, the boundary between the crust and the mantle. It is a little deeper underneath the continents, a little lower, however you want to say it, for a couple reasons. One, the continents do sit a little lower in the on the mantle. They float lower, they sit heavier, however you want to say it, they sit heavier than the oceans do. And as I like to half joke, well, there's also that much, more rock involved. The ocean floor is decidedly thinner than the continental crust. They are made of two different things. We'll get there at some point. I'm not sure if it's this lecture or not. So yeah, Moho-Rosich discontinuity, the boundary between the crust and the mantle. I don't know why there's no words there. All right. We also knew that inside the earth is warm, otherwise, more than likely, it would not still be molten in there. And, the generic answer has always been, well, it's the Earth's core that keeps it warm. Okay, but what about the Earth's core keeps it warm? And what we boil down to is whether or not you're in the core or you're anywhere in the Earth, radioactive decay. Okay, we talked about decay briefly when we were studying the periodic table a few lectures back, and we told you that many elements break down. They give off energy. That energy is quite often seen as heat, not always that horrible cancer-causing radiation that we familiarize ourselves with, that we've become familiar with over the years when we think of radiation. It also gives off heat. All right? A whole lot of things that come out of radioactive decay, actually. So we had one temperature-related vocabulary word already. It was lapse rate, okay, and that was change in decrease in temperature within the troposphere. We got one more for you now here, geothermal gradient. All right, and geothermal gradient is the increase in temperature as you go into the Earth. Don't worry about the rate, okay? Don't worry about the rate. And it doesn't seem, that warm that much. But again, if you remember, there's 5,280 feet into a mile. You can do a little math there and see how much heat you get out of 1 mile there. So As I indicated a couple minutes ago, there are exceptions to this rule. Every so often, the hot makes its way up towards the surface in the form of volcanoes and hot spots. A hot spot usually is what feeds a volcano. It's a pool of magma, unusually close to the surface. You'll hear about those again when we talk about volcanoes. And then the one bullet that I did skip over is very near the surface ambient. Well, what the heck does that mean? Well, this is something you're very familiar with. You even have to go as far as your basement to understand this one. There is sort of a ambient background temperature underground, near the surface underground, that is a good bit cooler and steady, all right, all year round. So I don't want to say that this geothermal gradient doesn't kick in right off the bat, but it kind of doesn't kick in right off the bat. You go down into a cave. Usually caves are nice and cool. You know the stereotype. So again, it's the same as with your basement. So we do have that, and that's the idea that heat pumps work off of as well. There's sort of something you used to hear about a whole lot more down south. I've been seeing billboards around here for heat pumps. They're an alternative way to heat and cool your house, and it's based on the idea that we have this more or less static temperature. I forget the number. I want to say like 65 degrees, something like that. And it's a good starting point for heating up or cooling off water instead of starting from, scratch. So yeah. We didn't mention the 9,000 degrees Fahrenheit. Again, not a number I'm going to quiz you on, but in case you ever wondered. Questions? Okay. That brings me right back to middle school. That was like so 1983. A lovely little diagram here. Now, when I was in middle school, we didn't have crust, mantle, core. We just had crust, mantle, core. I assume you guys heard about the 2 layers. Because we certainly would have giggled about inner core in middle school. But nowadays, this is fairly common. And, we've always, I don't think always known. They've known for a very long time, as long as we've understood the magnetosphere, that there was 2 layers to the core. But I don't think our teachers ever bothered with, distinguishing them in a diagram. So I'd like to think you can label this without me even pointing here. Well, it is labeled already, but when you walked in the door, none of you would put the core on the outside, the crust on the inside, hopefully. It is college, though, so we are going to step it up a bit. Oh, not yet, though. Sorry. We're going to talk about the crust. We're going to talk about each of these layers, then we're going to step it up a bit. Sorry. The crust. I mentioned a couple minutes ago, there's 2 types. You got your oceanic and your continental. I also told you that they are made up of different types of material. These 2 words may not mean anything to you just yet, but soon they will. The ocean is made out of a type of rock called basalt, and the continents are made up of a type of rock called granite. Now, some of you in the know may be thinking to yourselves, wait a minute. I remember hearing that limestone is a marine rock, and we got limestone all over the place because the oceans have been all over the place. Or you might be thinking to yourself, wait a minute, I've been up north where those rocks are sticking out, where the mountains came up in the Adirondacks there, and that is not granite. You're right in both cases. What we mean here is the deep down underlying foundational stuff. Okay? I don't even want to use the term bedrock because, that other stuff is sort of bedrock as well. But the very, very bottom, foundational cores. You've got the salt on the ocean, and you've got granite making the continents. And I told you that they sit a little differently as well. I'm not sure if that's a slide we're prepared to show here. No, we're not. So you'll see that later, apparently, where I actually have the densities. Again, it's not a number I require you to remember, but just so you can see, they are slightly different density, and that has a good bit to do with how they sit on the mantle, how they float on the mantle, how like ducks on a pond. So the crust. The mantle. Consistency of silly putty. Well, that seems a little weird, right? It's not very scientific. But again, we mentioned the other day that pressure and temperature do really weird things to materials. We were talking in the context of fluids the other day. Well, the same is true here for solids or semi-solids, whatever you want to call these things. We always use the word molten rock. The mantle is made of molten rock. And, you know, nobody's going to throw you in jail for saying that. But it's weird. And they use the term silly putty for a couple of reasons. One, silly putty is very malleable, as you know. All right. But they could have just as easily said Play-Doh or clay, right? So what's different about silly putty? What's different is the elasticity. I don't know last time you played with silly putty, or if you remember silly putty, but it bounces, it stretches, okay? And back when we used to actually get Sunday funnies in the newspaper, that was one of the fun things you could do before we had cell phones, is you take your silly putty, you press it onto the paper, it lifts up that cheaply based ink there, and then you could stretch all your favorite cartoon characters out and make them look all weird. All right, and then that silly putty would go right back to normal again. So elasticity. They feel that this rock behaves elastically. And again, for the geophysicists and the folks that study that, that is apparently very, very important. So that's why we say it. And then it makes it easier when we're talking to college students. They're like, oh yeah, silly putty, I know that. So it's very relatable. Okay, there are density changes. Again, we talked about going from the crust to the mantle, and that there were density changes, and that's how we recognized we hit the mantle. Well, there's even more in the mantle. And again, if this were a geophysics class, which thank goodness it is not, we would be recognizing the upper mantle, the middle mantle, the lower mantle, and telling you all kinds of wonderful things about that. As it turns out, we're really only concerned with the upper mantle in this class. And because of plate tectonics, you'll find out in a moment or three. So, the mantle and the core. So there's two cores. You've got the outer core, the inner core, iron and nickel. Okay, for the most part. There is a little bit of other stuff in there. Towards the end of today's lecture, I think we'll get there, you're going to learn why there's iron and nickel there. We mentioned the other day, well, I'm saying that a lot, I apologize, but we did mention the other day, the fact that the outer core is sloshing around the inner core and creating that wonderful magnetic field. And going back to silly putty for a minute, what I find is interesting out of all this is that they actually do freely use the term liquid here. All right, and they're not being careful to say molten or silly putty like iron. Right? They're like straight up legit saying liquid. So why the pressure argument doesn't apply here, I can't tell you. It could just have to do with the actual material we're dealing with. All right, the fact that it is a solid metal, not solid, it's a straight up metal. Maybe that has a lot to do with it. Whereas in the mantle, you've got silicate, you've got oxygen, you do have some iron and nickel. Don't get me wrong. You've got so many different ingredients. That might be the reason. I did forget at some point, I'm not sure if it would have been the other day's lecture, but I keep talking about how pressure makes things behave differently, okay? There's a really easy example of that you're pretty much all of you should be familiar with. If not, you can just run to Targets or Walmart after class and familiarize yourself. A gas grill, okay? Your portable gas grills and lanterns and a handful of other things take those little green bottles. We've all seen those little green bottles. All right. Anybody ever shaken one? You can do it. It won't blow up. What does it sound like? Those of you that have shook it. What's in there? And you may have the big white ones for your gas grill out back. You folks have maybe. You guys don't own grills yet, I'm guessing. But
I've never shaken one, so I don't know.
anybody shake one? Yeah, it's liquid. LP. And then one that says LP gas. Oh, LP gas. That must be a brand. No. Liquid propane gas. Well, wait, what's going on here? So you shake it, and it is a liquid. So you guys all have homework. You folks at home, too. Go to Targets, go to Walmart's, shake one of those little green canisters. You'll hear exactly what he does. It goes. Sounds like a can of Coke. But when you turn it on, it goes. It's not dribbling liquid all over the place. It comes out as a gas, right? So that it's the pressurization in there that changes that gas into a liquid, or allows the liquid to gasify. I'm sure if that's a word, but so that's the kind of stuff we're talking about. Pressure does really crazy things. And you learn about it in chem class, but not everyone quite gets that. So there's just an easy example to understand what we're talking about there. So if you're already a semi-solid and you apply those huge amounts of pressure, well, then it can make it almost, really solid. So, anywho, so that's what's going on here when I keep talking about pressure there. And go shake a gas tank. All right. So, like 7 minutes ago I said, but we're in college now, so we're going to move on to, we're there finally. Not just enough to be crust, mantle, core. We need to add the terms lithosphere and asthenosphere. All right, lithosphere and asthenosphere. Astheno is always tricky for you guys. That's not quite the consonant clusters that you're used to, but it is a fun word to say. You're going to get a mineral called sphalerite, which is also unusual consonants put together there. So the lithosphere is the crust, and remember we just talked about upper mantle, right? Crust in the upper mantle. I like to think of that as the eggshell and that little bit of goo that you just can't ever shake off of it, okay? That's about how much mantle is attached there, comparatively speaking. But it's important, again, to the folks in charge of this stuff, that it isn't just the mantle. It isn't just the crust. There's a little bit of mantle involved as well. Then below that is the asthenosphere. And I told you we weren't going to worry about middle mantle. Then I tell you, well, this is the middle mantle. I want you to worry about the word asthenosphere, not the word middle mantle. So, and you're going to see this in a diagram in a minute. The asthenosphere is the section of the mantle just below the lithosphere. And as we said, it's not all of the mantle. It's just sort of the middle section. So new diagram, updated diagram if you would. Tried to sort of stay with the color family. On the right is what we learned a little while ago. What's D? On the right is what we learned a little while ago. What's D?
Want us to just shout it up?
Sure.
The crust.
Crust. Good. Somebody else. What's C? The mantle. E. Which one? Inner core, and AB? Outer core. Excellent. So we knew that. Now we're going to add the lithosphere, asthenosphere stuff. And again, it may not be exactly to scale, but so A then is our lithosphere, okay? And B is the asthenosphere. So in that context, then we don't even worry about the rest of the mantle. Every so often, someone will ask me about AB. That is a function of scantrons. There is no F on a scantron sheet. Unfortunately, sometimes we have to put F's at the top. But in your bubble choices, there is no F. So when we used to take, in the olden days, before COVID, we used to take bubble sheet tests. If I wanted to have more than 5 answers, I had to get creative. So A, B, A, C, so on and so forth. And that stresses you guys out to no end, of course, because you've had 12 years of people saying, oh my God, only color in 1 dot. Because you will confuse that poor little machine. I don't use that machine. I grade those by hand. So the online folks sort of follow my diagrams, because I can, of course, go up to Z online if I want to when I'm making a test. But they've inherited diagrams that have A, B, and AC in them occasionally. You folks on campus, we haven't gotten back to take that vote yet on whether or not you want to take your tests online or on paper. But at any rate, so that same artifact does stand still. So crust, mantle, core, lithosphere, asthenosphere. All right. People sometimes get hung up on the alphabeticalness of it all, and they want to put asthenosphere on the outside, and also because there's an A there. Don't trip up on that, okay? Just sort of a unofficial heads up. Lithosphere's on the outside. Lith means rock, so if that helps, right? The rocks are on the outside. All right, just a wee bit about plate tectonics. Again, it has its own chapter. We talk in the first lecture about how science has changed over the years. Plate tectonics is definitely one of those things that has evolved. When I was in school, and the old joke about, the textbooks being 100 years old was true. I guess it depends on the district nowadays. I was in a decent district, but we still had really old textbooks. So we learned about continental drift, and that was in the 80s. And we should not have been learning about continental drift because they got rid of that 2 decades before. Teachers still use the word now, historically speaking, I think. I've informally surveyed over the years, whether you're down at Proctor or in Whitesboro or New Hartford, you still hear the word continental drift. But it's been plate tectonics for a while now. But what's changed almost more importantly is that it used to be the last chapter in every book. You get to plate tectonics, you get there. You talk about it a handful of times throughout the semester. But we throw it in at the end of the book. Well, now, criminy, it's like chapter 3 or something. And the paradigm change there is that, it is responsible for a lot of the stuff you're going to talk about during the semester. It's responsible for earthquakes, most of them. It's responsible for volcanoes, again, most of them. The mountains, the current location of the planets. The continents, sorry. So they move it up front, and they give you all the information about it, and then when you get to those chapters, you say, okay, so you remember plate tectonics, we told you this. So I don't know how long that's going to stick around. I've been teaching long enough that it was still in the back of the book when I started teaching. But I think that I front load you guys with enough information that we still save it for the end. And if, God forbid, we don't get to that chapter because we've spent too much time on another chapter or whatever, you're still leaving knowing the basics of plate tectonics because we've touched on it at the beginning of the semester and, again, a handful of other times. So if we don't get to it, this is your plate tectonic exposure. We know why it works or how it works. We're not sure what causes that to work, though. I'll explain in a minute. So the idea is that the lithosphere, not the crust. We're so used to saying the crust of the earth is broken into pieces. It's the lithosphere. We want you to acknowledge that the little bit of goo from the mantle is stuck to those crustal plates. And again, we're calling that the lithosphere now. So the lithosphere is broken into pieces called plates, and those pieces or plates are resting or floating on the asthenosphere. I mentioned ducks in a pond the other couple slides back. All right. And it's not quite that free, because when I say that, I'm guessing half of you pictured the continents floating around the ocean, which is only half the story. The ocean floor is plate as well. And they're not separate plates all the time. Sometimes they are. Like the Mediterranean, I'm fairly sure it has its own plate. And the Pacific definitely does. But North America has half the Atlantic attached to it. Europe has half the Atlantic attached to it. And there's other examples. So it's not just like that. A much better analogy or visual picture for you would be a pond with all the ice cracked. All right? Because you're not really free to slide anywhere you want to. You're bound in by the piece of ice next to you in this scenario. Those cracks, by the way, are called boundaries, or in this context, plate boundaries. Again, you've probably heard that word before. And that's where all the exciting stuff happens. Usually in the middle of the plate, it's pretty boring, normal. All right? But at the plate boundaries, where the plates can do a handful of things, they can slide by one another. All right? That gives us earthquakes. Even after all these gajillions of years, they haven't worn smooth yet. For you folks at home, I'm running my two hands side by side. If we could do picture in picture here, you'd see. It's very cool. All right? But it's still, after all these years, it's still not smooth. It gets hung up, and that hanging up and catching is when it finally pops. That's the earthquakes. Plates can also smash into one another. That does two things, depending on where you live or where you are. If you're talking about land to land, it makes mountains. So your two hands come together, your fingers go up. If you've got two continental boundaries touching. If you're in the ocean and they're coming together, they do the opposite. They go down. And we could sort of only semi-incorrectly say it's the weight of all that water that makes it go down instead of up. But you'll see why in a moment that that's not entirely true. So when two oceanic plates come together, they go down. When two continental plates come together, they go up. They call them trenches when they go down, mountains when they go up. Side by side is earthquakes. They can pull apart. That also gives you a trench. Sometimes. Actually, I just lied. Do not write that down. That gives you, again, a mountain range, depending where you are. It's not that simple. This is why we have a whole chapter for it. What do I want you to do in this context? Pulling apart, if you're an ocean, gives you a mountain range, a ridge as they call it.
Is it the longest mountain range on the planet under the ocean?
Yeah, it's the Mid-Atlantic Ridge, which is exactly why I should not skip over that. So, yeah. So when you've got oceanic plates pulling apart, it allows the mantle to seep up, and it builds mountains. If you have continental plates pulling apart, it does, as I said earlier, it leaves a giant hole, except they call it a rift. All right. And again, don't worry about all these vocabulary words. I'm just kind of fleshing it out for you here. Africa is being ripped apart on the central east coast. You know where Madagascar is. All right. I mean, you look at Africa, there's hardly any lakes in that whole dang thing, and then you get over to that area, and it's just riddled with big, long lakes. That's because it's very slowly being pulled apart. The water is able to come in over there. Madagascar used to be attached. Heck, India used to be attached. They really don't know what's going on with India. It's moving really fast. The last 60 million years, it has ripped itself off from Africa, turned, 90 degrees, and it's trying drastically to drive itself through Asia, throwing up the largest mountain chain in the world in the process there, at the surface at any rate, the Himalayas, which are actively growing every day. Did I cover all my boundaries? No, there's one left. Ocean to continent. All right, we have that on the west coast of North America. And so we will talk about that in great detail when we do volcanoes. Because again, believe it or not, we do have volcanoes in North America. They're just all the way over there. That is a special interaction. And what happens there is the ocean plate loses. It goes down. The continental plate stays up high. And if you've ever cooked at a restaurant, it's the equivalent of throwing a real icy thing right out of the freezer into the fryer. Anybody done that? What's it do?
That's a good idea.
Nobody's fry cook anymore? Good Lord, we need more fry cooks in the world. We need more SpongeBobs. All right. Well, I was a SpongeBob in college, and I can tell you that it's not good when you throw ice into a fryer. Don't do it. It's a bubbly, nasty mess. All right. And like I said, we'll get to that when we get to volcanoes. So that's your plate boundaries. Don't worry at this test about the different types of boundaries. All right. As I said, I'm just fleshing it out. You will have every opportunity to learn those later. Here are said boundaries. The big ones at any rate. We've got 7 large plates and many, many small ones. All right, not all of which are on here. You got North America there, almost in the center of the map-ish. And you see that mid-Atlantic ridge that we were talking about. It is a very long, very tall mountain chain. So tall, in fact, that it pokes out of the ocean every so often. Iceland. The Azores. Where'd Darwin go? I just forgot.
You went to the Galapagos.
The Galapagos, thank you. Handful of other island chains going down through there. All right, those are, Hawaii, we're not on that yet, but Hawaii has mountains coming up from the ocean floor. So that's really what an island is. It's the tippy top of a really tall mountain. So they're over there in the Pacific plate. You see how the Pacific plate comes back over to the other side of the map. And we told you the plate boundaries is where everything happens. Yeah, it's not always pleasant, especially for that whole region of the Western Pacific there. Okay, all those Pacific islands up into the coastal area there, just riddled with earthquakes and volcanoes. Okay, west coast of North America, we do have some volcanoes. We also are known for earthquake down there. Caribbean plate, every so often that rattles. Indian plate, we just talked about that one. So, Antarctica is its own little hunk of land.
Do you think Iceland's ever going to be like ripped in half because it's right in the middle of the 2 plates?
No, because of the fact that more magma keeps coming up to replace it. I mean, it's going to be constantly changing. It itself is, the island is a volcano. Several volcanoes, I think, several bits of it. But ripped in half, no. They used to talk about that with California. Will California get, ripped off of North America? That one maybe, because Pacific plate is moving in a slightly different direction than the North American plate. But that would be a cataclysmic event in, more like tens, if not hundreds of thousands of years. It's not going to be like one. Hollywood would make it a 2-hour movie, of course. But that bit that sticks down Baja California there, that's the strip we're talking about. That's attached to the Pacific Ocean all the way up to San Francisco, basically where San Andreas' fault. And then everything above the San Andreas fault is attached to North America. So that's what all the hubbub is there. Half of it's, not half, but part of it's on the Pacific plate, and the other part's on the North American plate. But, if you'll allow me to wax philosophical momentarily, some folks will say that Atlantis, if it did ever exist, if you go back and read some of the earliest writings about it, Plato and whatnot, the demise that Atlantis made is very equivalent to how some of these tiny little islands go out of existence, earthquake and volcano blowing themselves to smithereens and sinking and crumbling into the ocean. Not to mention that a lot of those writings go back to when the glaciers had left, about 10, 12,000 years ago. And we see a lot of these coastal cities and towns just completely inundated. Again, some folks who want to argue sea level rise and so on and so forth are the same folks who were sitting there on the weekend watching the Discovery Channel and watching people explore these villages that are now 70 feet underwater. They didn't build them there. That was dry land when they made those villages, and it was just before the glacial melts. So it's not crazy made up science, folks. I find myself saying that way too often anymore. But just so many logical inconsistencies out there these days, where people will love this, but then when you turn it this way, they don't like it. It's the same thing. And I am actually premised with this, but it's my wrap-up slide. Plate tectonics is so important because it's responsible for, like 4 chapters out of your book and then some. And then some. All right. We're switching gears now. So before we move on, any questions about what we'll arguably call the geophysics nature portion of this lecture? You guys all want to stretch before we move on? Yawn and stretch. Yawn at least. There you go. I heard that. I'll just sip more coffee. Okay. I'd put one of those let's all go to the lobby slides right there. So as I said, switching gears to something else that I really surprisingly and shamedly forgot to mention a couple semesters. How old is the Earth? And this is more important than ever because it's still so many folks aren't really sure what to believe. And again, we don't use the word belief in science. So if you guys want to believe that the Earth is 6,000 years old, I am never, ever, ever going to change your minds. And that's fine. I don't need to. When I ask you the question on the test, and you need to remember that you're in a science class, I simply ask that you choose the science class answer. Whether you believe it or not. So despite all of the numbers on here, if you ask me, I'll say it's about 4.5 billion years old. And by throwing that about in there, I'm ignoring the 0.54 there. I'm ignoring the 4. And I'm ignoring what I always write on my tests, and on this slide here is that it's 4.6. All right. But again, when I give you this question, I'm not going to put 4.4 billion, 4.5 billion, 4.6 billion. I don't play that game if you haven't figured that out by now. All right? It's going to be billions, millions, trillions, who knows? It's about magnitude, right? And our magnitude that we need to work with here is the billions. And that, my friends, is based on the age of a meteorite. You may find yourself saying, well, why are we basing the age of the Earth on a meteorite? And if you don't know that answer, you will soon. There's a couple reasons, really. Oh, by George, it's right there. We're able to do that because we believe in something called the solar nebula theory, which I will tell you all about. And the solar nebula theory tells us that basically, again, in that geologic fuzzy rounding world, everything in the solar system is the same age. Okay? Not wave a wand, poof, there's a solar system. Everything is time stamped at 3:55 p.m. kind of thing. No. No. But in the realm of, let's say you had $4.5 billion in your bank account, are you going to worry if you're 35 cents over or under, whatever? No, right? So we have these relative magnitudes of error that we're used to working with. I premise that a little differently. Let's say you've got $5 in your wallet. I don't even have $5 in my wallet, but I don't play with paper money anymore. But let's say you usually have $5, okay, in your bank account. You're going to be watching every single little nickel and dime, right? That's your level of magnitude where you're concerned with. If you had $5 million in your wallet, you might not be so concerned about those nickels and dimes, let alone the fives, maybe even the 50s. If you had $5 billion in your wallet, you see how this grows. All right. So when we say the same age, we mean that in the relativistic terms of 4.5 billion years old. Yeah, what's 50,000 years? Okay. So close enough. Close enough. There she be. Lower left-hand corner, we've got the wonderful hunk of rock. We've since confirmed this with many other hunks. Don't worry, this was just the first one. It left this amazing crater in Arizona. And just to get you a little bit of scale, there's the visitor center. Oh, you can't see my mouse. Kind of see my mouse. There's the visitor center. So that's one hunk of crater. It was formed about 50,000 years ago. And again, it's just kind of the first one we tested. We've again confirmed time after time again on these meteorite fragments. We've gone out to space, grabbed some ages and dates there. So before we get on to this, the question I guess I'll throw out to you guys, why do we need to use a piece of space junk to tell us how old the Earth is? Why is it helpful at any rate?
Because it's not going to be likely to move.
What do you mean?
I mean, if it hits it, it's either going to be...
So again, let's assume we believe in solar nebula theory that tells us that we can use a meteorite. That's out of the equation now. Not really why can we need it. Why do we kind of need to?
Because if it's floating around out in space, chances are it's probably from around the same time that the Earth was formed together.
Yes, that's true, and that's why we can use it. Anita, why do we need to use it? Why can't we find a 4.5 million year old rock on Earth?
Because the position of the rocks changes, and the rocks can change from different forms.
Getting there. We're getting there. Somebody add to that. We're getting much closer now. All right, because of 4.5 billion years of weathering and erosion. All right, we've found bits and pieces. I want to say the oldest hunk that we found so far is 4.3. All right, so he was kind of on it with it's been out in space. If he had stopped there, perfect. The thing is there's no weathering and erosion out there, short of you come through the atmosphere and you're going to get ripped apart a little bit. But that's essentially pure, untouched material from the first moment, if you would. It hits, it's a big enough piece, we're golden. Down here, you've got all that sedimentary rock, first of all, on top of everything else. Sedimentary rock is recycled, right? Over and over and over and over again. So when they do find these bits and pieces, they're tiny. Okay, talk about needle in a haystack. This is literally it. And then some. This is a broken needle in a haystack. So they're finding these little quartz crystals that are that old. Okay, but again, finding them is the tough part. So when we do find them, they happen to agree with this idea, which is great. That supports this idea then. And also, that gives us more data and more evidence to support solar nebula theory. So we do have rocks that have been around that long. They're either buried due to weathering and erosion, or they're broken down into such teeny tiny pieces, parts, and included in other rocks due to weathering and erosion that makes them really hard to find. But every so often we do stumble upon some, and as I said, when I last heard, we were right around 4.3 or 4.4 billion. We haven't quite hit that 4.6 that we see in the meteorite chunks. All right, so what is this solar nebula theory? The idea is that our sun and the solar system around it formed out of a nebula. Okay, well, solar nebula theory, we got sun, solar, and nebula in the definition. That really doesn't help a whole lot, does it? So what's a nebula? A nebula is a cloud of gas and dust that can be both the beginning and the end of a star. It's a stellar graveyard, it's a stellar nursery. And as I said, it is our sole argument for barging on ahead and talking about cosmology, possibly in the next lecture. Nebulas are left over after supernovas. Somebody remind us what a supernova is.
A star exploding.
Right. A star exploding, which creates so much heat that we're able to fuse elements that otherwise would not have existed. Okay? Stars, basically speaking, fuse hydrogen into helium. Everything else gets built in the star as it ages and or dies. But for the most part, it's all hydrogen and helium. Now, a star can go up to iron without exploding. But our periodic table goes way past that. So, and again, I'm going off task here. I'll try to come back to this. But it's all that gas and dust that is left behind after a supernova explodes. And that gas and dust isn't just riffraffy crap laying around. It's elements, okay? It's all elements. Over time, that nebula, that cloud, will start to condense. Some properties of gravity, all right, that we'll go into a good bit more, again, if we do that section of lecture. They start to condense, and once two or three pieces stick together, because of gravity, it's that much more likely to get more stuff to stick to it, and it's sort of a logarithmic snowball rolling down a hill thing from there. It just starts going, and at one point, it collapses in, sparks it up, and you've got a star glowing. Yeah.
Have we ever actually seen that happen though?
Which aspect? Not in real time, no. We've seen, they've seen, I'm guessing, very snapshot versions of it. Okay, we look out there, we see nebula everywhere, all over the place. And we see them in various stages of their growth. And yeah, you're absolutely correct. We've really only calculated that those are the heats that we would need to fuse stuff beyond iron. But once we calculated that, we also saw, oh my gosh, there is stuff beyond iron there. And well, we have our planet, for example, that has stuff as well. But no, none of this sadly happens in real time, mainly because of the distances. And I was confused on this, and I still don't really truly understand it. But supernovas, when we see, well, one just exploded, or one exploded, there's a famous one that exploded over China. They saw it, the Chinese recorded it years ago, before we were paying attention over here. They're not in real time. Because of the amount, remember we told you it takes, 8 or 9 minutes for light to hit us from the sun? Okay? These things are so damn far away that we're seeing them hundreds, if not thousands of years later. So the concept of real time in astronomy practically doesn't exist. And that is a shame, because I briefly thought or understood it to be that supernovas were so freaking huge and hot that we would see them, somehow it didn't obey the speed of light or something. I don't know. But But no, I've come to accept that even those we're not seeing in real time. We say, hey, it just happened last night for us. For wherever they are, it happened years ago. So, but yeah, loosely answering your question, we've seen evolutionary snapshots of these in multiple stages to enough to be able for them to say that, yeah, this is how it happens. And we know how gravity works, and so on and so forth. Great question. So what is this solar system? All right, our solar system, in our case, planets, dwarf planets, asteroids, comets, and moons. All right, planets, dwarf planets, asteroids, comets, and moons. You're probably aware Pluto, for example, no longer a planet. Okay. Once we classified Pluto as a dwarf planet, they started getting recognition to these other bodies that we'd been looking at, many of which are bigger than Pluto. And so we do have a handful of dwarf planets out there. In Earth science, we go into that a good bit more. In geology, not so much. Comets, those are the icy bodies. Moons, typically those are terrestrial, rocky. All right. Some of them were captured due to gravitational pulls. Some of them, like our moon, was actually due to a collision. Another planet about the size of Mars-ish, which is a good bit smaller than us, just for reference, smashed into us, and the debris went off to make our moon, is what they feel now. There's a nebula. You ever bored one day? Google nebula pictures. They are so neat, so varied. They make great wallpaper on your laptops, etc. I don't think this one looks like a crab. But the cat's eye nebulas, what they call them that? Boy, those do look like cat's eyes. And there's a horsehead nebula. You see a crab in there?
Yeah, the top is like the top of the crab. The bottom left, it's got like a claw shape.
Okay. Well, I won't argue it. I'll smile and nod. Oh, yeah, I see it. But maybe it's my angle up here. I never quite see it the right way. But yeah, they've named them all. All right. And because of spectroscopy, we know that certain gases glow certain colors and so on and so forth. We know it's in there. They know it's in there. I say we like I was, they consulted with me. I don't know what color yellow is, but folks in charge do, right? And that's how we know this stuff. Certain things glow certain colors and so on and so forth. Again, they're not making this stuff up. This is in Taurus, 6,500 light years away from us. So again, when this thing exploded, it took a really long time for the dinosaurs to say, whoa, what was that? All right? It takes a while. Oh, we do have a slide for supernova. So again, supernovas are important because they allow, the heat in these things allow for fusion beyond iron. So we get more and more elements. And if you look at stars then as elemental factories, you start to understand or appreciate the idea of generations. All right, we told you, that a star will burn hydrogen to helium, and that's pretty much what they do. So that gets you 2 elements out of the 100. Well, where do we get the rest? All right. Supernova isn't the only way to die. It is a great way to make, though, as we said, elements. But it's like Legos. You don't jump straight to, some element that's way towards the end of the periodic table. It slowly but surely fuses, and then the next time it explodes, you're fusing more and more complex elements. And then the next time it explodes, each time it makes these nebula. The nebula contract, form a star with a solar system. It lives out its lifespan, and it explodes again. And that's really stretching a lot of your brains out. I get it, because that's a lot of time we're talking about here. I truly, as I said, still ponder some of that stuff some days. It's a lot of time. But it's a way that makes sense to explain how we have what we have today. And there's other angles that support it as well. So going back to the nebula for a minute, all right, we only need the hydrogen for the star. So everything else that was left over from your nebula is going to start condensing on its own. It doesn't go into the star. And over time, with it smashing into one another, again, the same gravitational rules apply. 2 or 3 pieces is that much more likely to attract 2 or 3 pieces, and then they're that much more likely to attract 6 or 10 pieces, and so on and so forth. And the next thing you know, you've got all these rocky bodies floating around. Same thing happens with gases. Gases could clump together. You may have wondered why we have the terrestrial planets closer to the sun than their gaseous planets. It's because of density. Okay, the more mass you have, I should say mass, the more mass you have, the more you're affected by gravity. So those terrestrial planets weren't able to, well, let me rephrase that. The elements that eventually formed the terrestrial planets weren't able to escape as far out due to our sun, but the star's gravity. But the lighter elements were able to go a little further out. So they congregated further out. I keep saying the sun, and this, of course, is a conversation about our solar system, but this is and can be true for any star out there. Okay, there are millions and millions and billions of solar systems out there. This is just ours. And again, depending on where they are in their stellar evolution, we're about 3rd or 4th generation, they feel. In order to have the elements that we have, our sun has gone through its cycle 3 or 4 times. Which means, yes, it will do it again. You all won't be here. It'll slowly but surely expand out past Mercury, then Venus, then we're 3rd stone from the sun, right? Then Earth, and just past Mars, it'll envelop all of those before it contracts back down and explodes out again. So somebody won't be happy on Earth when that happens, but you guys won't be here. Horrible, scary vocabulary words. Centrifugal force, conservation of angular momentum. Let's just call that a merry-go-round. All right? You guys remember merry-go-rounds? I know they didn't have, but you've seen them on TV, right? There was like one in Utica when my son was growing up. They basically outlawed them because my generation and the 90s kids didn't listen to the playground instructors. But you've seen one, right? And I don't mean a carousel, a merry-go-round. What? Carousel is horses you ride on up and down. A merry-go-round is basically a circle with bars on it that freely spins around. And you're supposed to wait for it to stop to get on, wait for it to stop to get off, but we never did that because it's way more fun to jump off while it's moving and jump on while it's moving. And we were actually just doing physics, but they didn't appreciate that. So I see enough of you smiling, nodding, you know what I'm talking about. So what's going on here is exactly that. When you jump on, that instance that you add your mass and your trajectory to that thing, it goes just a little bit faster, right? That's what gets this all swim. What's it doing? Circulating. Spiraling. There's the word I'm looking for. That's what gets this spiraling, okay? Is these things come in, they add their mass, and it just gets it spinning around. Well, that spinning around will eventually, it's weird. First it causes it to condense a little bit, but then it actually causes it to stretch out. And that stretching out is the part where it's also fun, is when you let go of the merry-go-round while it's still moving, what do? You go, woo, you fly out, right? That's the stretching part. Now, we're not going to tell you which one of those vocabulary words is which. Again, that's for your physics teacher. But that's the reason why this all happens. So, the ball of gas condenses, and then it thins out. And like I said, your lightest stuff, your hydrogen, goes into the star in the center, and everything else just sort of density separates out. And over time, those rings condense. We get our rocky bodies. Let's see where we're going here. 90% of the material stays in the center, forms a star. Remaining 10% goes on to form the planets, etc. Yeah, I do have the word there, accretion. Accretion is what they talk about when you're building planets, the rocky bodies. The asteroid belt between the outer planets and the inner planets. All right, again, there's a reason it's there. I think there's still a lot of folks studying it exactly, but it's more or less the stuff that never came together to build rocky planets, or they were rocky planets and they broke apart. There was a lot of collisions going on, assuredly. But at this point, they're just kind of caught in orbit like satellites are above us. Okay, there's a certain point where they just say, okay, we're just going to float around here in a circle. You've got all those obligatory fly-through scenes in your movies and everything. My wife always just said, well, why don't they just go up and over? That's not exciting Hollywood, that's why. You could go under, too. So this explains or describes the formation of our solar system, but that's really not my point. My point, the reason I'm telling you about all this, is because of where we started. This is why we could say that everything in the solar system is approximately the same age, about 4.5 billion years. And what's cool about that is that's one less variable in the equation when you want to talk about stuff. We mentioned a couple planets already. We've got Venus, one stone closer to the sun. We've got Mars, one the opposite direction. If they're all sisters, all right, they're all roughly the same age, why does Venus look like it does, we look like we do, and Mars looks like it does? Yeah, you've got the difference from the sun. There's one variable. Venus and us are about the same size. Mars is a good bit smaller. So there's another variable. So that's enough to work with, right? Venus has a huge, horrible atmosphere. We've got ours. It's pretty cool, arguably. Mars, not so much at all. There's so many things we want to compare and contrast. And if we can remove one thing from the equation, that's great. So that one thing is solar nebula theory allows us to say they're all about the same age. There's your solar system. I still, to this day, am 50-50 guessing whether it goes Jupiter, Saturn, or Saturn, Jupiter. I can't get that one down. But the rest of them I've pretty much got. And some of you remembered, like mnemonics that your teachers gave you. My very good mother did something, I don't know what, something about pizza. But, is that Bivens? Hello. Sorry. Friend of my son's. And they didn't draw the asteroid belt in, but the asteroid belt goes right here between Mars and Jupiter. And bless their hearts, they put Pluto in there too. It's probably an old diagram. Questions? I don't know that I'll be able to answer them necessarily, but you never know. Yeah.
Why does Saturn have?
Because it's snazzy.
Not a lot of other planets. None of the other planets are
Actually, is it Uranus or Neptune or both of them? They just never made it into pictures.
Oh.
It's a little more common than we thought.
Is that because they're farther from the sun too, and the sun?
I don't remember the reason for it's got a huge gravitational pull. No question about that. So whether or not that's riffraff, again, the same kind of reason I explained here. It's like a mini solar nebula theory going on, maybe, but it is not the only one with rings. I learned that a couple years ago. But yeah, it is just riffraff that it pulled in. It's they've each got, some of them have 2 dozen, 3 dozen moons. It's amazing. And again, mostly just gravitationally attracted stuff. So you got a bit of a taste for some of the weird cosmology stuff here when I was talking about nebulas and whatnots is, again, you guys think about it. When we come back in next week, I'm going to ask you, do you want to hear about cosmology or not? And we might just pretend it's a democracy in here. We'll see. All right, we got a couple minutes left, I hope. Oh, yeah. Okay. My watch is just going nuts. All right, so 4.5 billion years ago, I'm just going to read this. 4.5 billion years ago, the material that our Earth is made of coalesced in space. We already used the word accretion, so it accreted. This material was elements from the periodic table. When it first came together, it was a molten ball, or it was a big fiery ball. Again, picture your favorite sci-fi movie. Somewhere in there, there's a big flaming evil planet. I know a lot of the superhero ones recently. Marvel had a couple of those. All right, Star Wars has one too. We looked like that. Okay? We were held together by gravity. And of course, everything cools off eventually, right? I like this picture. This was probably somebody's thesis. But, so we will go from glowing fireball to bits and pieces start to cool off. All right, and those are the gray or the blacker areas on there. That is the beginning of our crust. Yeah?
What caused the pieces to cool off?
Well, just exposure to just like how like cafeteria pudding gets that skin on it, and it just, stuff cools off. The inside, as we know, hasn't yet. That's one of the things they're working on with Mars, is why doesn't Mars doesn't tectonic anymore. Mars is solid, or darn close to it. They're a good bit smaller than us. But again, the same age, so their elements should still be radioactive, going through the decay process. So there's probably more to it than we know. There's always more to it than we know. But that's a simple question. Is just because it's exposed to space out here, it's going to cool off. There's no wind, but for an outside example, it's just, the outside of stuff cools off faster than the inside of stuff. I don't have a better answer than that, sorry. But yeah, it definitely cools off from the outside in. All right, just picture a cake you're baking too. You touch on it's good to eat, and then you go to cut those brownies, and it's still super hot inside, and you should have waited a little longer. A lot of it comes through with the fact that you're insulated on the inside as well. That keeps that. It's not telling you why the outside cools off, but it is an argument for why the inside stays warm longer. Is that you're insulated by your own materials in that sense. But just exposure to the cold, hard void of space, as we were talking the other day, allowed the surface to solidify. And like I said, we know, because every so often the Earth still cracks open, she bleeds. We know that it is not solid all the way through yet. Hopefully it never will be, at least when we're doing our thing. Plate tectonics, is a good thing, because when that stops, probably the rotation of the core will change a little bit, and we might get too much radiation through. So I don't want to weave stories right now, but it wouldn't be good for life on the Earth. So, homogeneous accretion theory, probably the biggest word of the semester, but it's really not that scary. Homogeneous, as lots of folks like to say. Homogeneous, okay? You don't buy homogenized milk, you buy homogenized milk. So, homogeneous accretion theory tells us that when we were that flaming ball of goo, it was just a mishmash. Everything was all messed up. You would probably assume that. What we mean is it wasn't layered, like we just spent 10 minutes teaching you. Those layers had to grow, had to form. Okay? So originally everything was homogenized. That's what the deal, it means same. Homo means same. Okay? So we had to undergo, and this should be in bold print as well here, density separation. That is a vocabulary word. At one point, we underwent density separation, and what happened there? Undo bold, undo delete. Yeah, what did I do here? Okay. How many of you had a glass of orange juice recently? I'm looking at this, so I'm going to assume at least a couple hands went up. What is the first thing you did presumably before you poured yourself a glass of orange juice? You shook it up. How come? Because all that yummy good stuff is at the bottom. Exactly. The pulp is at the bottom. That pulp, which, by the way, is a good bit more dense than the water in the rest of it. That's why it's settled out. All right? That's all we're talking about here with density separation, is the heavy stuff settles out. The difference between that jug of orange juice and the earth is that the earth is a ball, a sphere. So out is the center. Down is the center. So remember earlier I told you, we explained why the iron and the nickel is in the center of the earth and not up at the surface. That's your orange pulp. Okay? That's some of the heaviest stuff we got in there, and it sank down. Again, over time. This all takes time. So we were a big pile of goo all mixed up. It sat here. It started to cool off. As it's cooling off, stuff is settling. We grew our layers. Okay. On the test, we use the words differentiated and undifferentiated, and I'm seeing that I don't actually use those here. And I should, because they're two test questions. So differentiated means different. Undifferentiated means not different, right? So which one is not different? Homogeneous or what we have now? What we have now is differentiated. Okay, homogeneous is undifferentiated. I don't know if those words used to be in a slide and I somehow accidentally deleted them over the years. So our layered earth is a differentiated earth. Good. Just got a few more slides. I apologize. You guys have been at this for a while here. So at about 3.5 billion years ago, this is 1 billion years after it formed, by the way, the crust cooled and shrank. To compensate for that, the crust cracked. Go to the onions next time you're at the grocery store, and you see how the onion skin cracks as the onion grows. Okay, it is the sort of the opposite of that. The inside of the earth is still hot, so it hasn't shrunk. But the outside, as we just explained, cooled off, so it shrank. The only way for it to still compensate for the inside of the earth around it is to put these little cracks in it. All right? Those are our plate boundaries, our original first plate boundaries. And we just don't have it. Do we go to 11 or 11 something? All right. I was really hoping to fit this in, but I don't want to rush it. All right, we'll have a part 3 on this one.